sorry. Just destroyed it. Yeah, it's okay. Yeah. I contributed to the issue with my partners from Easy City Architecture and Design Research on the idea of computational intelligence, which is slightly, I would say, an investigation about, in the new kind of production which are made available by grid computing. So if we take a look at what is my main concern, I would say that it's knowledge. It has been knowledge for a while, I would say. Since I really started when I entered the discipline of architecture. But one of the main questions which is asked to us at the moment, it's this, actually. I think this is probably a very stimulating question. We are living in a society which is dedicated to knowledge and intelligence per se, with this kind of cognitive society and cognitive capitalism. But the idea is that I really wanted to make an experience in my own work in the way this knowledge and in the way truth can be assimilated bodily. So in a sense, the whole investigation which is dedicated to computational intelligence is a part of it. It's a part of this question. What is the place of the human if the sole reason for living is to know? And what is the relation between knowing given by machines, knowledge given by machine and knowledge given by humans? So if we take a look at two sentences, and the first one, the oldest one, is from Grundrisse in the fragment, from Marx in the Grundrisse in the fragment on machines. And of course he's saying that knowledge and scientific knowledge in the first place is the principal productive force at the moment. So in collective intelligence, most of the time we put a lot of emphasis on knowledge and intelligence which is produced by human interactions. And my concern here was the analysis of knowledge and production, which is the result not only from human interaction, but also from just purely computational and scientific interactions. And as it is said, in '96 by Don Tapscott, we see that the digital economy is an economy based on the networking of human intelligence. But back to Marx, we see that scientific knowledge is maybe a more precise category. So you have this wide knowledge, cultural, scientific, etc. But the scientific knowledge, I should say, has a place which is a bit apart of it, apart in the production process. So if we go back to, let's say, pure science, like mathematics, we see here two images. One of the geometry room at the University of Göttingen, which is probably one of the main moments in the rising of mathematical knowledge, since Felix Klein was responsible of this program, and then he moved to the US for a series of conferences in 1893 in Chicago, and it was really an important moment in the rising of American mathematical science. And we see, of course, this Vutumas school on the right. So let's follow this question from Felix Klein, saying that, this question is really related to collective intelligence as a human phenomena. He's saying that would it be possible to create an abridged system of mathematics adapted to the needs of the applied science without it being necessary to go through the whole field of abstract mathematics. And of course, when we take a look at what is used today, I should say that we cannot really evaluate the impact of these elements on the collective intelligence, because those books are a proof of the rising of collective intelligence, but at the same time they are part of the reason of it. They are some kind of cause for this collective intelligence. And this was planned, in a sense, by Felix Klein a century ago. So if I keep a bit on the side this human collective intelligence, what about the computational one? I mean the computational paradigm. So it goes in two ways, actually. You have first a distributed paradigm and then an integrative paradigm, which are really part of this computational collective intelligence. So the distributed paradigm, the example of it is given to us by Hilbert-Zeimer when he asked what was the impact of the electrical grid on the evolution of the production and on the evolution of contemporary society. And it just said that the electrical network was a real force toward decentralization. And today, we see the same kind of analogy in grid computing. And researchers are asking, how analogous are they with electrical grids? What is the relation between grid computing and electrical grids? And I mean grids, actually, in the history of architecture, as we can see here, was, of course, mainly, I mean, extensively studied, especially in the year 60s, by Andrea Branzi. And we see that on the left we have this kind of modernist grid, which is, let's say, an unproductive grid. And we see that on the right we have this plug-in grid, which could be either an electrical network or either a grid computing infrastructure. And this grid computing infrastructure actually is invented by the CERN in Geneva. It's really under development at the moment. It's widely operational, that I will show. And I should say that it's the basis of something which is as important as the first generation of internet. So we have the Web 1, and Web 2 is about grid computing and infrastructure. And that's what is said here. I mean, we see that scientists are speaking about grid computing, which is at the same time an integration exercise, and which also presents significant challenges in harnessing distributed resources. So it's really about the, I mean, let's say the convergence of two models, the distributed model and the integrative one. And if we enter this kind of collective intelligence economy, we all know that, for example, you have really precise problems that cannot be addressed by human intelligence. I mean, for example, these protein folding problems require a huge amount of computational power. And that's what is said. And we see in this declaration about the NAW Grid project, which is about economic and on-demand brain activity analysis using the worldwide grid. I mean, you have two main technologies, Nimrod-G and GridBus, actually. And then they are just saying that we are facing a lack of computational power within an organization for analyzing scientific data and the distribution of knowledge. So we are using parametric technologies, parameter specification languages, and we are also trying to integrate resources. So this is a map of a grid computing, which comes from Gridscape, actually. And we see here what I'm calling an image of an ambient factory. So you can have this image which comes, for example, from the internet network connection, which I would say are not qualitative maps, because you can have those images where you see which part of the network is in use, actually, who is connected. But here, this map is showing something slightly different because it's showing the resources which are available for computation. And that's what you see here when you are using just that kind of software for parametric computing. So you see that you have the host here, and you know precisely where they are located in the world. You have here a second category of hosts. I mean, Legion and Globus actually are it's almost like brand. I mean, it's systems, grid computing managing systems. Then you fix your own deadline, and then you get the cost. And that's the way you distribute, I mean, the work you need to see computed through the network today. And I will show you a bit later on really precise example in contemporary industry regarding this. And here you see, for example, a work regarding biotechnologies. So it's a doc application parameterization for virtual laboratories. So you just have a molecule which has to be screened. Then you give a job execution order, and you get the result. So actually you have different things. You have this computational turn with all those disciplines which became computational. You have a need for new standardization to make sure that the computer can communicate all together. And then you have a new deployment of the post-industry. So actually, what I'm just trying to show here is that the collective intelligence is also part of a new deployment of the idea of production, of the idea of factory, and of the idea of living as well. Because what we see on the right is that this SETI at Home project, it started as an experiment, almost as a joke, I would say. I mean, searching for extraterrestrial intelligence. But then all the industry started to see the economical potential for this. And this last one, for example, Models at Home, it's a project which is initiated by Daimler Chrysler, sorry, which is made for computing the crash test, I mean the deformation of the car body through the world. So, I mean, while speaking, maybe some of the computer which are in the next building are working for Daimler Chrysler at the moment. So this is a new interesting evolution of the idea of what is a factory and what is production. So this is a view of what I'm calling this ambient factory. And actually this is a correspondence of the collective intelligence, but which is a physical image of the collective intelligence. And this is a second image of this collective intelligence, and actually, as we see, the shape has no importance. I mean, has no importance. It can be square, it can be groovy, it can be just anything. And if you just go back to those researches, research in the year 60, then you see really beautiful anticipation from Bronzy, for example, because you have the square model on the left, the groovy one, but actually you have the same infrastructure, you have the same kind of capitalism, and you have the same kind of computational intelligence. So actually this computational intelligence asks for new standards, and that's what is said by Negri and Hart in Empire, actually. They are saying that we participate in a more radical and profound commonality than has ever been experienced in the history of capitalism, and we need common languages. And those common languages are the XML revolution. So the XML, and I'm quite sure that really soon we will have an XML language for architecture, which will probably allow architects to communicate on a different level of abstraction through the world. So maybe the collective intelligence will enter a new step. We will not only exchange files coming from Maya, from Mathematica or Rhino, but maybe we will have a new standard which will allow the computer to interpret, to understand this mathematical or geometrical information in a much more efficient way. And of course, this standardization is absolutely not new. It's part of our history of science, and it's part of the history of industry. And we see here that, for example, at IBM, they just say that technology relies really on standards. And we see that today, if we take a look at the Web 2, what is called the Web 2 revolution in a sense, with the wiki system, with WordPress, with all those mashups softwares, we see that everything relies on standards. And this is what is said here as well. Since XML can define the meaning and structure of the information, enabling computer tools to use that information directly. So it's about a separation of style from content, presentation from structure, and design from data. So actually this new standardization allows us to put everything together, because it's great to distribute the intelligence everywhere, but it asks for answers. How can you integrate different knowledge in a really efficient way? Because, the creation of a new knowledge is only the result of the integration of pieces of pre-existing knowledge, actually. The only way to move forward in this knowledge-based economy, it's to be in this kind of perpetual integration system. And here, that's what was, the first integration paradigm came from the revolution in the CPU, in the fabrication of the CPU. And then we have a different integration paradigm. So this is presented in the AD issue. So we have language, we have a wide use of the capabilities of the inorganic materials, like a silicon-based chip, for example, is an example of that. And you have, for example, a DNA computer, which is the result of the use of the organic material. When you put all this knowledge together, what we know about languages, computer languages, etc., what we know about the property of inorganic material, and what we know in the organic material sciences, then you are entering a new field of the economy. And this field of economy actually is highly dependent of the communication between different kinds of knowledge and intelligence. And this cannot be solved by human systems, because the quantity of knowledge which is necessary is absolutely not, it's far beyond the capabilities of thinking of any human mind, actually. So we see that those things like peer-to-peer, for example, are used as well. So you have the merging of peer-to-peer of grid computing as a next generation computing platform for solving large-scale problems through sharing and aggregation of geographically distributed resources. And you have this diagram. So you have the formal languages, the distributed production and distributed computing. And then you see the new role which is played by the open technologies, for example, which is played by the grid technologies or the peer-to-peer technologies, and which is played by the standardization of languages. So just by showing this diagram, I want to show, for example, that things which can be, for example, peer-to-peer or open source are part of a redeployment of a global economy. They are not alternative models, actually. They are just part of the regular economy. And that's what is said here. For example, you see, I mean, in this really interesting article, you see this person who worked for IBM in Linux for more than 6 years and saying that it has become big business for them. So it's a fundamental part of IBM business. We are not into Linux and open source because it's cool. It's nice that it's cool, but it's good business. We are making billions. So, I mean, actually, the interesting thing is how we can go toward a new understanding of capitalism by understanding the new role and the new impact which is played by alternative technologies. I mean, what was planned, of course, to be alternative technologies like peer-to-peer and open source. And for example, here you have a list of material, which is, let's say, the result of the very beginning of the collective intelligence, the human collective intelligence. It was published by Hannes Meyer in the Bauhaus Review in 28. And here we see that, I mean, we see a list of corporations active in the biomaterials. And here we see, for example, only a list of plastics. And we see the evolution, I mean, the quantity of material. And this quantity is made possible by automated discoveries. Actually, when you go at DuPont today or at Bayer, you see those big chemical corporations. What you see is that they are using the grid computing to accelerate the discovery of new materials. And they are using statistical methods to make tests and to see if those materials are efficient or not. And the collective intelligence here, the human one, is, I would say, more into the side of pure concept than on the side of production. So we go into this kind of separation between two kinds of intelligence which meet, of course, from time to time, and that's a really important aspect of it. But quantitatively speaking, they do not lead to the same production of value. I mean, the main value today is produced by the automated discovery processes more than the collective intelligence. I just show you a couple of sample works because I want to make it short, but I show you a couple of examples on these grid computings. You see, for example, all of you probably know Arcelor, which is the second largest steel company in the world. And you see that Arcelor now is using the grid computing to create new kind of steels. And you see 90% of the grid computing work leads to new discoveries. So this is an example. Then you have AstraZeneca. All of you know AstraZeneca, which is one of the leading groups in the pharmaceutical industry. And you see that they are also using grid computing platform to accelerate drug discovery. And you see platform computing and that, etc., etc., which is as well an example of this. You see the same kind of experience at Novartis, distributed desktop grid. PC refresh helped Novartis enhance innovation. And I could continue this actually completely endlessly. And for example here, which is about the merging of peer-to-peer and grid computing as two complementary technological apparatus. And for us in architecture, you see the evolution of CATIA, for example, which is as well really interesting. And CATIA is now investing a lot of money in grid computing solutions. And they are searching for a loop of global optimization which asks for thousands and thousands of CPU. So you have this new definition of the production which is based on different concepts which are not widely used in the field of architecture usually. You have this distributed computing, this integrative paradigm, the concept of optimization, which is of course really important because it's all about optimization at the moment, and the way you are dealing with the separation between the creation of concept and the creation of value and the creation of automated discoveries. So I show you a sample of works which which will light on the use of the grid computing techniques. So it's it's a project about a chair. It's a chair design project. So we use these techniques. It's about using genetic algorithm actually for optimizing a structure. So you see here the optimization of a traditional cantilever in 2D. So you see that the representation is really simple. It's a binary representation. Where you have the 0, you have no material, and where it's 1, you just have matters, actually. The internal representation, it's a bit more, is a bit more evoluted than that. Let me just find it, sorry. I think it's that one. You see, for example, this work, this research work that we have led in the field of architecture is a collaborative work done with those two persons, Atem Amda and Marc Schonauer, from the École Polytechnique in Paris. Actually, they developed something really interesting regarding topological optimization using different kind of internal representation. So you have this first level of representation, which is the binary one, which is really simple. And then you have this second level of representation, which is based on Voronoi diagrams. But the Voronoi diagrams actually are used only for representing the crossover operation in the genetic algorithm mutation. So they are not used as a formal tool or as a, let's say, geometrical tool, but as an abstract mathematical tool which is only used for the internal representation. So that's why you won't see, in a sense, Voronoi shapes in that. And actually, I think it says something interesting regarding the generic character of some of the mathematical tools which are used today in the field of architecture. Because, for example, with the Voronoi diagrams, you see you see plenty of application of it. And you see that some researchers are using them for their precise geometrical or structural performances, and some other researchers are using them only for optimizing the internal representation of the algorithm in a purely algorithmic process and memory allocation, etc. So I think this as well is, let's say, it leads us to some kind of a new epistemological situation in architecture, which is not based around the idea of models. It's some kind of an anti-idealist situation, because you cannot use a model as a traditional model, you see, like as a biological reference or something like that, because it has so many applications and so many abstract usage by mathematicians that you cannot use in the way we did it, let's say, even 20 years ago. So here we see different things regarding those chairs. It was done by, by using Mathematica. It was just about computing contours, etc. And here we see those different models. So the idea was to start with a block of matter, the most stupid, massive block of matter that you can imagine, and then to remove voxel by voxel some part of it. So for each generation, actually you have 100 individuals. So for example, the model which is on the left, which is 860 generation, it corresponds to 86,000 structural evaluations. This is really the point of it. And because of that, because we produced 25 chairs, which are all different, and because each chair has something which is, let's say, as an average value, about 65,000 structural evaluation with the finite element method, you can easily imagine that a single computer cannot do it. So that's why we used distributed computing technique at the École Polytechnique. So here we see different images of this T1 model. And of course, we had, let's say, some kind of traditional aesthetical aims or wills for this work. I really wanted it to look as the most primitivist object as you could imagine, in a sense. I don't know if it really looks primitivist at the end, but I was interested by the contrast between the highly technological level which was engaged and the highly scientific and mathematical level of knowledge which was necessary for this project, and the fact that there is a strong discrepancy between what you can obtain, visually speaking, and the mathematical basis which is present in an object. And I think this is only something interesting in the evolution of the contemporary architecture, is that the traditional correspondence between, let's say, a building which could look like futuristic, like in the 60s, and the level of knowledge which is shared in a society, like in our Occidental civilization, actually, is not obvious as it was before, because the abstraction of mathematics is becoming so high that you cannot deduce from a mathematical model a visual model. You have just too many things which are implied in between the first step of the project and the final result. And here we see the 25 models of those chairs, and we see this kind of ecology which appears. We could produce actually 1,000 or 2,000 of chairs. It wouldn't be that much of a problem at the moment. It's only a matter of computation. And we are working on a second version of this project, which is in the continuity of the first one, still using genetic algorithm. But actually, in this project, the genetic algorithm were used to optimize the structure directly with an abstract representation based on Voronoi diagrams. And in the upcoming project, we are using the genetic algorithm to optimize not the structure, but the robot which produces the structure. So every time we are just trying to go from a certain level of abstraction to a level which is higher, actually. And we just lack this discrepancy, because the higher you go in the abstraction of the concept, and I think the closer you are to what is really happening today, in a sense. I show you a really final image, and I go through that. I'm sorry. It could have been interesting, but I think it's already late. And I think this collective intelligence, I've presented those images of American housing patterns. I think this collective intelligence in the future has some fair chance to manifest itself in this kind of really primitive houses. And this is the one that Ludwig Wittgenstein has built himself in Norway. And actually the discrepancy between the really high level of technology and high level of knowledge, which is ever growing because of the collective intelligence processes, and the way we are living is going into something which I think is that direction. And we were just searching for that in the chair project. Okay, thank you.
Just do something fast. I mean, don't you want to do it? But these things always run behind. You know this. Oh, let's assume I can open mine.